So if you are waiting like for a polished conference-style talk, then it's definitely not it. So actually, this is more like a stand-up talk. Like I have no slides whatsoever. I have some code demos, and basically, I just wanted to give you like a quick introduction into machine learning. So who knows what machine learning, or who does not know at all what machine learning is about? Okay, so most of you are like a little bit familiar with the thing, which is good, and I guess it's also like because in the recent month there was a lot of fuss about machine learning. So basically, what machine learning is all about is that normally we write code, we write functions to solve problems, right? With machine learning, we turn everything around and say we just we create a neural net that is like a little bit working like the brain, and we throw data at it, like big data, and then the neural net actually it will learn from the data. So the neural net comes up with a complicated function, basically. So let's put this into context. So anyone knows the Prisma app? So anyone used that? No? Okay. So basically, when we look at this, we can think, okay, this is just yet another filter app, right? So it's just like we have some pictures and we put some nice filters on top of it. But technically, that's not really what happens here. So technically, what happens here is that we turn like regular pictures into art that is inspired by real artists. Like, for instance, we can take a picture and we can turn it into a piece of art that is like as if Michelangelo or Picasso would have made it, right? And we call this a style transfer, right? So we basically take the style of an artist and apply it to some picture. And the way that works, so a regular filter app basically just transforms a picture, like applying some transformations on the original picture, like make everything gray but keep the red things red, so you have a nice red ball in a rest grayish kind of picture, or these kind of things. But what happens here, and I can bring up some before and after, so that we see like this one is like the original picture, right? And this one would be like the piece of art that is generated. So, and what happens here is that basically the picture is really recreated on a blank canvas, right? It basically not just shifting pixels in a way that it transforms them. It's really like recreating these pieces of art. So if you ask like a student in who is studying art, right, and you show him a picture and you ask like, okay, can you paint this in the style of Van Gogh or something, and it's a good student, then probably maybe they can do it and get close to this, yeah. But if you try to actually write software that does this is a pretty complicated task, right? This is not easy at all, right? Writing functions that do this, and like another use case that is like not easy to solve with traditional programming is like self-driving cars, for instance, right? If you think about what it takes to drive a car, and for most of us it comes quite natural, right? So a long time ago we've been to driving school and we just do it naturally, but it's actually a very, very complex task. And these kind of things, so these problems that we are tackling today are so complex that it's not easy to solve them with traditional programming, right? So what we can do and what people are doing, and in fact like NVIDIA is really, really strong when it comes to machine learning. So they blogged about how they actually make like a self-driving car, like a basic self-driving car, with end-to-end machine learning. So what that means is they basically take a video input, right? So they drive with cameras mounted on the car, and they also collect the information from the steering and from the pedals and everything, like the inputs, how much accelerate and how much do you brake, and they feed that into a neural net. So a neural net, they blog about this here intensively, like what exactly are the steps that they are doing, and like a neural net has, like I said initially, it's a little bit like a brain, or at least we think about this as a simplification that is that we have connected neurons. So, but the general idea is you have this neural net, and you just feed in the data, like a massive amount of video material together with the instructions of like the steering commands and all this, and then the neural net basically figures out all the hard work it takes. Like, for instance, should I slow down if, like, in front of me red lights are appearing, or like how do I actually like follow the road and everything? The neural net eventually will figure out these things. So this is not like the only way how to solve self-driving cars, but what they explain here in their blog post is really an end-to-end approach. So really just feeding in the raw video data into the neural net, and the neural net will basically learn how to drive the car, right? So this is pretty amazing stuff, and it shows that you can tackle problems with machine learning that are too hard basically to tackle with traditional programming, right? Okay, so this is like the high level overview that I wanted to give you about machine learning and why we want to do that. And maybe also there's a company called Comma AI, for instance, and what they do is they give you an app. You can mount that in your car, and it's like a dash cam, and they upload all these video material from all the users who have this in their car. I also used to do that, and the neural net will learn from all the data, all the video data from all those people contributing with this dashcam app, right? So over time, the neural net learns how to drive a car just by looking at the sheer data, right? All right, so that's the fast introduction of what machine learning is about, and what I want to show you, what I want to demonstrate you is so I've been working with some friends on a new platform we call Machine Labs, and it's a platform where we want to make it easier for everyone to get into the field of machine learning, because the problem with machine learning really is that it's not easy to get into right now. So the first thing is the whole approach of machine learning is you take this big data set, and then you have like a training, and and this training is it takes some time and everything, and so it's not easy to actually do that on your own machine if you want to do something serious, right? So because you need a special setup, you need special hardware power, like you need a good graphic card and everything. So this is why we wanna tackle this with a platform. I go into that a little bit more in a moment. Maybe just like one thing I wanna also demonstrate is like to give you like the very basic idea how a really naive implementation of machine learning works. So this is like machine learning in 22 lines of code. So what we do here is just to give you an idea of what machine learning looks like in the inside is, we have basically a goal that we want to achieve. So in this case, we want to have a goal prediction of 0.8, right? And we have an input, right? That is our starting point, and we want from the input we want to go to get to the goal prediction, right? So and how a neural net learns, and this isn't really a neural net, but how a neural net learns is that you have basically in the neural net you have like something like variables. We call them weights, right? And the weights are the neural net takes your inputs and combines them with weights and goes through an activation function, and basically it then calculates how bad it performs. So in machine learning, we are not so much interested in like how good we are. We always measure how bad we perform. So we measure the error rate, right? How much are we off from our goal? And in very simple terms, we can basically we can look at it like this. So we have our input, and we just multiply it with our weight. And all weights at the beginning, they are just random. So if you have a neural net that is just beginning to learn, all the weights will be just random, right? So and then we calculate. So we have the input, and we multiply by the weight, and then we calculate the error. So how far are we actually off from our goal? So in this case, we are just taking the prediction minus the goal prediction, and then we are I'm missing the word for that, if the English word, if you square? Yeah, we are taking the square of this. So why are we taking the square? Because we always want to have a positive error rate. Because if you are like missing your goal by 2 points or by minus 2 points, it's still missing it by 2, right? So you always want to have a positive error rate. So this is why you taking the square to make the numbers positive, right? Okay, so then we have our error, and then this is a super naive approach. But what we do here is basically we look, okay, if I change my knob, my weights here, my knob rate. If I change this, if I increase it, will the error actually go down? And if I decrease it, or if I decrease it, will then the error go down? So basically, I'm just looking if I tweak it in either direction, will this make the error go down or not? And we will just do that in a loop, and you can see that basically we start here at the very beginning. So we have a prediction here of 0.25. We have an error rate of 0.3. And then you see that basically it is just adjusting the weights, and the error rate is going lower. And at some point, we are pretty close to our prediction that we want to have, right? So our goal prediction was 0.8. So this is in a we can do questions at the end. Yeah. So in a nutshell, really, this is like the very basic of what machine learning looks like. In fact, in a neural net and in like frameworks where you implement neural nets, this is not exactly what's going to happen, but it gives you an idea like what like the basic the basic functionality of a neural net, how it works. All right, so of course this is not like real code, but if you want to work with some real framework, there are frameworks like Keras. Keras is a machine learning framework that sits on top of TensorFlow. So TensorFlow is probably the most popular machine learning framework that we currently have. And then it looks like this. So you have so in this case, for instance, what we want to do is we want to teach we want to teach the XOR gate, right? So the XOR gate basically goes that if you have like two negatives input, then the result should be negative. And if you have two positives, then also the result should be positive. Should be negative, sorry. And if either one of them is positive and the other one is negative, then we also always want to have a positive outcome. So basically, you see here that this is our training data, and this is our expected outcome. And then we build layers in our neural net where we have where basically in these layers there are then the weights that the neural net tweaks for us, right? So it's pretty much comparable to the simplified code that we've just seen. So we still have like an error function that calculates how bad we perform. It's just that we don't have to define this stuff ourselves. So this is called a loss function. So we calculate the loss. This is the actual term for that. And you see there are different loss functions for different use cases, but this is exactly the same what we just did. It's the mean squared error. So calculating the squared error rate that we have. And then we have like an optimizer that is actually like tweaking the weights, and there are different kind of optimizers. And depending on the use case, depending on what you actually want to do, you configure different activation functions, different loss functions, and all this. Yeah, but this is like the basic principle. So then you define the number of epochs. So the training always works in epochs, and with every epoch, the weights are tweaked until we get to the desired state. So here also we can look at the very beginning. We just ignore those warnings here in the beginning. So basically we start and we have a accuracy of 0.5. So that means that 50% of our predictions are actually wrong, right? And you see that we are actually even decreasing. So in the beginning, our neural net is performing very badly. It tweaks, and the accuracy is actually decreasing. But if we keep going here, we will see that it makes the right moves with weights, and eventually it will actually learn the XOR gate. So if I look at the very end, then we see we have a 100% accuracy, and it makes the right prediction. So if we look at this output here, we see that we make a prediction here with the training data, and we know that if we give this training data, we want exactly that output, and this is exactly what we get here. Of course, this is really just like absolutely dummy code. You would not do that. An XOR gate is something you can put in a map, and you directly get the results that you want. But this is just to demonstrate how this learning actually happens. So what we do here with this platform is we give you something like a online code editor, like a JS Fiddle or something, where you can perform this code. We can make a new run to see it live. If the server is actually running. Oops. Damn it! I have this open in a tab that is incognito, so I'm not logged in. So let's make it here. So now I have an actual run. So, and we can see this is now starting. It's going pretty quickly. But yeah, basically this is performing now this code on our server. And so the idea here is to also give people a platform where they can run these experiments, where they can share them, where people can just go and fork them. This will always run on like blazingly fast hardware somewhere in a data center with graphic cards from NVIDIA that are actually actually made for this purpose of running neural nets. And yeah, this is what we hope we can improve this whole experience and accelerate the machine learning efforts to make it easier for everyone to get involved. Okay, so yeah, I think this was my quick machine learning talk. And if you have any questions, then I'm happy to take them. Yeah?
How is, I know it's just an example of simplified neural network, but how is it actually different? When you look at it, it looks like a normal least mean square filtering or Kalman filter or something like that. I mean,
What exactly?
the code that you showed.
Which one did this?
The first one or the second one. I mean, what is actually the difference between doing a least mean square filter or a Kalman filter for that matter?
Well, it's really just like you are setting up these neurons in the network. So here, this is creating a model that behind the scenes will set up different layer, yeah, that will that will then have neurons, and you are configuring how these layer look like. Like this is, for instance, this is a very, I mean, we are throwing, basically we are shooting with cannons at problems that you would not really tackle with machine learning. This is just really like to give you a basic idea. But you can imagine that the inputs would not be a simple array with two numbers. You can imagine that you take a picture, for instance, like
Complex data structure.
you can, like any picture, like this stuff we've seen with Prisma, you can basically represent with numbers, right? You can you can have like a just like a matrix, right, of numbers, and then you have in each matrix you have another array with R, G, B, the values, the color values and everything. So we can represent basically everything with these numbers, right? And then it would go through layers which are also a little bit more complex, and then each layer would look at different parts of the image, for instance. So if we try to teach a neural net to recognize cats and dogs or something, right? Then we first give it some training data that is also annotated, so it knows, okay, this picture is a cat, and this picture is a dog, and this picture is a horse or whatever. And it will figure out on its own how to adjust the weights, and we will have this on different levels. So these are all the different layers. So then you have, for instance, the first layer, and this is all doing it by itself. The first layer will start, for instance, to look at very basic shapes. Like does it have a shape like this, just like something a long shape or something, or is it like this kind of shape? And then the layers in that are on a deeper level will start caring for things that are more fine-grained, like oh, does it have a tail, or does it have arms or something? But this all happens completely without further ado. You don't have to do anything for that. It's just that the neural net will figure out these things on its own, because it's just over time recognizing these patterns. Okay, yeah.
Do we know some good sources where we could find the information if we want to just learn a little bit more than how to create a quite complex XOR gate?
Yeah. So. What you can do is, for instance, in the, I think in the Keras. So Keras is the library that we've just seen, and I think we have. And by the way, there are also like plenty of really good data sets out there. Like there are from Udacity, there are data sets for self-driving cars. So you have like tons of video material that is also annotated and everything that is ready for you to play with. There are like tons of annotated YouTube videos and everything. So there's really tons of data for everyone to play with. I think maybe let's just Kara's GitHub. Some good. Yeah, there are examples. So here are, for instance, some better examples, and like one of the this is also like a bit like the Hello World. I mean, the XOR gate is the very basic Hello World, and if you want to go one step further with Hello World, then you take the MNIST. So the MNIST dataset is a dataset with hand-written digits, right? And you can take this to actually make your own, to train a neural net to do handwriting recognition, right? So you can see like the code that it takes to do this, and notice that machine learning code, the code itself is not that difficult if you go into machine learning, because the whole difficulty really lays inside of the neural net, right? This is where the magic happens. So basically, when we look at the code for these things, then it's more like bringing the data into the right shape and everything, right? And then you see that we have like we are configuring our neural net. So this part is really like configuring our neural net. So here you see, for instance, so we have images, and then we are configuring here how like if you look at an image and you want to analyze it, then a neural net takes subsets of this image and starts analyzing this. And you are configuring these kind of things, like how big should the subset be of the image that we are looking at. You want to have something maybe like dropouts. So dropouts is basically a concept where you randomly take out some neurons so that they don't activate. It's a technique to prevent overfitting. So sometimes you have the problem that when you do machine learning, that you are throwing data at a problem, and the neural net really just starts memorizing the data. So it's really good at making predictions for this particular data, but if at some point then you come with different data, like a different cat picture, and obviously it should have learned how a cat looks like, but it does not recognize this other cat very well that it has not seen before, then this is what we call overfitting, right? And there are things like dropouts to prevent overfitting. So these are like tweaks in the neural net, in the model that you set up, right? And yeah, there are tons of good examples. I think, there are a lot of examples that go with images. There are also, here's a neural style transfer. So this is basically a Prisma, right? A neural style transfer is transferring the style. So take the style of Van Gogh and apply it to some image. Yeah? So here you can see basically the code that it takes to do a neural style transfer. And again, most of this stuff is not overly complicated, because again the really complicated stuff is handled by the network actually.
Okay, so I think we're on to the next.
Yep. Thank you very much.
So we'll do one more speaker, and then after that we'll have some sessions outside. Yeah, and maybe a quick notice is that software.